Hey everyone, and welcome to The Explainer. We all lean on GPS pretty much every day, right? To find a coffee shop, navigate some new city, but behind that little blue dot on your screen, there's this secret world of just unbelievable precision. We're talking about a science that can find a location not just to the right street, but down to the width of a pencil line. Seriously. So, yeah, let's dive in. I mean, just stop and think about that for a second. That is the kind of mind-blowing accuracy we are talking about. It sounds like something straight out of science fiction, but this is the reality of modern satellite positioning. So today, we're going to pull back the curtain and see exactly how they pull this off. All right, so to get to that incredible millimeter-level precision, we first have to wrap our heads around a kind of surprising truth. The distance your GPS first calculates, it's never perfectly correct. It's a fantastic estimate, for sure, but it's always contaminated with these tiny, unavoidable errors. And scientists have the perfect name for this almost right distance. They call it the pseudo-range. That pseudo part is everything. It means it's not the true, clean, geometric distance. Because you gotta remember, that signal's journey from a satellite 20,000 kilometers up in space, it's a messy one. So what's messing with the signal? Well, it's a whole list of tiny little culprits that have huge effects. You've got nanosecond-level timing errors in both the satellite's super fancy atomic clock and your phone's much simpler clock. And when you're dealing with the speed of light, a nanosecond is a big deal. Then, the signal itself gets slowed down just a tiny bit as it punches through the Earth's atmosphere. All these things stack up, and that's what creates that pseudo-range. Okay, so with all these little gremlins in the system, how does your phone even get a starting point? Well, it starts with the first and most fundamental measurement technique. This is the one that standard GPS relies on every single day to get you in the ballpark. It's called the code pseudo-range, and you can think of it like this. A satellite sends out a little digital package, a coded signal, with a timestamp on it. Your phone receives it and checks the time it arrived. By figuring out the travel time and multiplying by the speed of light, it gets a pretty good idea of the distance. This is the absolute workhorse of GPS. And you can see right here how well it works. For the civilian CA code, the one our phones use, we get an accuracy of about 3 meters, which is pretty good. It'll get you to the right house. The more precise military P code gets that down to about 30 centimeters. Better, for sure. But that's not going to tell you which pocket your phone is in. For that, we need a quantum leap. So to get from meters down to millimeters, we have to stop thinking about the timing of the signal and start thinking about the signal itself. And this, my friends, is where things go from impressive to, whoa, that's crazy. This is the big pivot. That signal coming down from the satellite isn't just a packet of data. It's a high-frequency radio wave, and it's oscillating billions of times every second. So instead of timing the whole trip of the package, what if we could just count the exact number of waves between the satellite and us? That's the precision you get, 2 millimeters. That is the potential accuracy of this next technique. It's just an astonishingly small margin of error. This incredible method is called carrier phase measurement. So if the first method was like timing a delivery, this is like counting the exact number of rotations a delivery truck's tire makes on its journey. It's not about when it arrived, it's about the microscopic details of the trip itself. And here it is, the billion-dollar question, the catch. When your receiver first locks on, it can measure the fraction of the very last wave that arrives with unbelievable precision. But it has absolutely no idea how many millions or billions of full waves came right before it. In the world of satellite science, this is the great puzzle. It's called the integer ambiguity. It's like we know the exact change in our pocket down to the last penny, but we have no clue how many dollar bills are in the wallet. Without knowing that whole number, that integer, our super precise measurement is basically just floating in space, completely unanchored to reality. So this is the core of our problem. We've got 2 tools. First, the code pseudo-range. It's reliable, it's unambiguous, it gives us a real answer every single time. But it's noisy, and it only gets us within a few meters. Then we have the carrier phase. It is exquisitely precise, down to millimeters. But it's ambiguous. It's a perfect measurement, but it doesn't have a starting point. What do you do? So what's the solution here? We've got one good but imprecise tool, and one amazing but unreliable one. The genius isn't about choosing one over the other. The real magic is using some seriously clever mathematics to make them work together as a team. And that solution is this beautiful process called differencing. You can think of it as a set of brilliant accounting tricks. By comparing different measurements in very specific ways, we can make all those errors we talked about earlier, the clock biases and the atmospheric delays, we can make them just vanish from the equation. Let's walk through the playbook. It's actually really cool. Okay, step 1. You have 2 receivers on the ground looking at the same satellite. By comparing their data, you realize the satellite's clock error is identical for both of them, so you can cancel it out. Gone. Okay, step 2. Now you have 1 receiver looking at 2 different satellites. This time, the receiver's own clock error is the common factor, so you can eliminate that. Poof. But the real masterstroke is the double difference. You mathematically combine those first 2 steps, and now, both the satellite and the receiver clock errors are gone. It's just this incredibly elegant way to clean up the data, leaving us with a much, much purer signal to work with. So now our data is clean. We've used math to basically erase the major errors from the equation. Now we're finally ready for the final, almost magical step, the one that really delivers the best of both worlds. And it's called carrier smoothing of the code. Here's what we do. We take our reliable, unambiguous code measurement, the one that gets us within a few meters, and we use the incredibly precise millimeter-level data from the carrier phase to smooth out all of its noise. It's like the precise data acts as a guide, refining and polishing the reliable data until it is nearly perfect. And there you have it. We solved the great ambiguity of the super precise method by anchoring it to the reliable ballpark method. And the result is the holy grail of positioning, a final measurement that is both unambiguous and accurate to within just a few millimeters. So why does all this matter? I mean, who cares? Well, this level of precision unlocks our future. It lets surveyors map land with centimeter accuracy. It provides the critical timing backbone for global finance and communications. It's the absolute foundational technology that self-driving cars will need to navigate our streets safely. And, get this, it even lets scientists watch the continents drift in real time to better understand and predict earthquakes. So the next time you look at that little blue dot on your map, just remember the secret science working behind it. It's this incredible dance between 2 different measurements, a puzzle of ambiguity and the elegant math that solves it all. It really makes you wonder, doesn't it? Now that we have this power, this almost godlike ability to know location down to the millimeter, what are we going to build with it next?